వెళ్ళదు మన డబ్బు వాళ్ళు ఇచ్చిన దానికి ఉంచుకోమని
ఈ డాలర్లా
మనకి ₹1 రూపాయి ₹2 బిళ్ళ ₹5 బిళ్ళ ఎట్లా వాళ్ళకి సెంట్ మన బట్టి వేసుకుంటా మనకి ₹1 రూపాయి ₹2 ₹5 బిళ్ళ ఎట్లా
ఇవి సెట్లు నోట్ అంటే ఒక
XRD analysis, X-ray diffraction, typical XRD pattern of indium oxide nanoparticles prepared by the chemical method. The XRD study indicates the formation of indium oxide IN2O1 nanoparticles. From this study, considering the peak of diffraction angle of 450 average particle size has been estimated by using the Square formula. D is equal to 0.89 lambda by beta cos theta, where lambda is wavelength of X-ray, 0.1541 nanometer. Cu Kn radiation, beta is FWHM, full width at half maximum, 0.011 radiation. Theta is the diffraction angle, 30 degrees, and D is the particle diameter size. The average particle size is calculated to be around 12 nanometer. Thus, using XRD pattern, we are able to calculate the particle size. XRD patterns of nanocrystalline AN2O3 samples using neem gum calcined in air for 2 hours. UV visible spectroscopy principle. The UV radiation region extended from 10 nanometer to 400 nanometer, and the visible radiation region extends from 400 nanometer to 800 nanometer. Now, new UV near UV region, what is the wavelength means? 200 nanometer to 400 nanometer. For UV region below 200 nanometers. For UV radiation spectroscopy is studied under vacuum conditions. The common solvent used for preparing sample to be analyzed is either ethyl alcohol or hexane. The possible electronic transitions can be graphically shown. Antibonding, non-bonding, and then bonding. Energy states from sigma to pi, then n pi dash sigma dash. Sigma to sigma star is nothing but sigma electron from orbital is excited anti-bonding orbital sigma star. The energy required is large for this transition. Methane has C2H bond undergoes sigma to sigma star transitions or shows absorbonic maximum at 125 nanometer. Pi to pi star, neta to sigma star. These transitions requires less energy than sigma to sigma star transitions. Now, chromosphere, the part of a molecule responsible for imparting cold are called as chromospheres. The part of a molecule responsible for impairing cold are called as chromospheres. NOT N double bond, NO2 N double bond, O C double bond, O C double bond, N C triple bond, N C double bond S, and C double bond C, etc. To interpret UV visible spectrum, non-conjugated alkanes show an intense absorption below 200 nm and are therefore inaccessible to UV spectrometer, and non-conjugated carbonyl group compound give a weak absorption band in 200 to 300 nanometer region. Next, oxochrome, the functional group with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromosphere alters the wavelength of intensity of absorption. Benzene, lambda maximum 255 nanometer, phenyl lambda maximum 270 nanometer, and aniline lambda maximum is equal to 280 nanometer. Now that what it is when absorption cathochromic shift, red shift, when absorption lambda maximum of a compound shifts to longer wavelength is known as redshift. That is nothing but OCH3 group exhibit redshift. Next, hydrochromic shift, blue shift. When lambda maximum of a compound shift to shorter wavelength, it is known as blue shift. It is due to the presence of a group which causes removal of conjugation or by the change of solvent. Example, aniline shows redshift in acidic medium. Hyperchromic effect. When absorption intensity epsilon of a compound is increased, it is known as hyperchromic shift. Example, pyridine, and if it is decreased, it is known as hypochromic shift. It is used for characterizing aromatic compounds. It is used it is used for characterizing atomic compounds. It can be used to find out molar concentration of the solute under study. It is one of the important methods to detect impurities in organic solvents. Detection of isomers are possible. Next, molecular weight can be used by using Beer's law. IR spectroscopy. Infrared spectrum is an important record which gives sufficient information about the structure of a compound. It is unlike UV spectrum, which consists of relatively few packs. This technique provides a spectrum containing a large number of absorption bands from mm, which we can get the information about the structure of a material. The absorption of infrared radiation causes the various bands in a molecule to stretch the band inflations. Another vibrations in another 2.5 micro to 1.5 micro 15 micrometer can be detected in the IR spectrum region. The region from 0.8 mu to 2.5 mu is called near IR, and the 15 mu to 100 mu is called IR region, and the characteristic stretching absorption bands appear above 1500 centimeter. Principle of IR spectroscopy. The absorption of IR radiations causes an excitation of molecule from a lower to the higher vibrational level. The IR spectra is a vibrational rotational spectra. All the bonds in a molecule are not capable of absorbing infrared energy, but only those which are accompanied by a change in dipole moment will absorb in the infrared region. Such vibrational transitions which are accompanied by a change in the dipole moment of the molecule are called infrared active transitions. Thus, these are responsible for absorption of energy in the infrared region. When infrared light is passed through the sample, the vibrational and rotational energies of the molecules are increased. Next, stretching, monochromator, amplifier, motor, and spectrum, and then infrared spectrometer. In this type of vibration, stretching, in this type of vibration, the distance between the two atoms increase. Symmetric stretching, the movement of the atoms with respect to a particle. The movement of the atom with respect to a particle atom is a molecule is in the same direction. Asymmetric stretching. In these vibrations, one approach the positions of the atoms change with respect to the original bond axis. Bending vibrations are of two types: scissoring, rocking, ragging, and twisting, wagging and twisting. In the vapor state, the absorptional band of stretching and antimolecular which is in turn occurs at high wave number when the same substance is in the solid state. Instrumentation, infrared light radiation from the source is split into two beams. One of the beam is passed through the sample under examination is called sample beam. Mm, the other beam is called the reference beam. When the beam passes through the sample, it becomes less intense due to absorption of certain frequencies. Now there will be a difference in the intensities of the two beams. If I not be the intensity of not be the intensity of the reference beam and I be the intensity of the beam after interaction with the sample spectroscopy. The absorbance of the sample at a particular frequency is A is equal to log I naught by I, and transmittance T is equal to I by I naught. A is equal to log of quantity. Intensities of the bands can be recorded as a linear function T against the corresponding wave number. Intensity of the two beams are converted into and measured as electrical energies with the help of detector thermophile. Applications of IR spectroscopy, identification of an organic compound, mm, structure determination, qualitative analysis of functional graphs, distinction between two types of hydrogen bonding, quantitative analysis, study of chemical reaction, study of ketone latomerism and complex molecules for determining the conformational analysis, detection impurity as a compared and compound and rotational isomerism, applications of electron microscopy, something scanning electron microscope, transmission electron microscope, atom light source, slate, condensing lens, object lens, macro image, projection lens, final image, scanning electron microscope, ECM, electron gun, magnetic condensing lens, magnetic object lens, magnified image, magnetic protection lens, image, etc. Now, the images electron microscope is produced by a scanning the sample with focused electron beam and detecting the secondly back scattered electrons. Electrons and photons are emitted at each beam location and subsequently detected. The schematic representation of some shown in figure. The electron gun produces a stream of monochromatic electrons. The electron stream is considered as the first condenser lens. Inverts as conjugation. It works in conjunction with the condenser aperture to eliminate the high angle electron from the beam. The second condenser lens forms the electrons into a thin, light, coherent beam. Objective aperture further eliminates high angle electrons from the beams. A set of coils acting as electrostatic lens scans and sweeps the beam in a grid fashion as in TV. The beam dwells on points for a period of time determined by the scan speed. Dwell time is in meters per second range. Now, the objective lens focuses the scanning beam into the part of this specimen. When the beam strikes the sample, interaction occurs before the beam moves to the next dwell point. The various instruments housed to measure various interaction, count the number of interactions, and display a pixel on a CRT. The intensity of display is determined by the interaction number. More interactions give a brighter pixel. This process repeated until the grid scan is finished and then repeated. The entire pattern can be scanned 30 times per second. SEM gives useful information on one topography, second morphology, and third one composition, and fourth one crystallography information. Transmission microscope TEM. A schematic representation of a TEM is shown in figure. Each part of the labeled and their functions explained below. The electron gun produces a stream of monochromatic electrons. This stream in focused to a small coherent beam by the first and the second condenser lenses. The condenser's aperture knocks off high angle electrons. The beam strikes the specimen. The transmitted portion is focused by the objective lens into an image. Objective aperture enhances the contrast by blocking out high angle diffracted electrons. Selected area aperture enables to examine the periodic diffraction of electrons by an ordered arrangement of atoms in the sample. Intermediate and projected and projector lenses enlarge the image. The beam strikes the phosphor screen and image is formed on the areas of the image represents the thicker or denser sample areas since these areas transmit lenser electrons. The brighter area the image represents thinner or lesser dense sample areas since the areas of transmit more electrons. Time image of the aging particles reads in XRD. XRD nanoparticles are spherical in shape with a smooth surface morphology. The diameter of the nanoparticles is found to be approximately 50 nanometer TEM. Image shows the produced nanoparticles are more or less uniform in size and shape. Image shows the produced nanoparticles are more or less uniform size and shape. Time image of aging nanoparticles. Source electrons, condenser, aperture, objective, and object, camera, eye, detector, flow screen, monitor, computer. Next, atomic force microscope. Atomic force microscope is used to investigate electrically ion conductive materials like proteins. In 1986, Binding and Thortio demonstrated for the first time the ideas of AFM, which is used an ultra small probe tip at the end of the cantilever. In 1987, Ramsing et al. Developed an AFM setup with a Pareto cantilever technique, which is used to light level mechanism. The intrinsic adhesion between tip and sample. There is another one from the capillary neck condensing between the tip and batter meniscus interface from the humidity. Electromagnetic interaction between tip and sample. Next, the electrostation interaction is caused by both the localized changes and the polarization of this substrate due to potential difference between the tip and the sample. It has been used to study the electrostatic properties of samples such as charges on insulator surfaces of ferroelectronic domains. Magnetic interaction, it is caused by magnetic dipoles both on the tip and the sample. Next, contact made by dynamic mode. In contact mode, the detection of the cantilever is kept constant. Contact mode AFM consists of raster scanning the probe or sample while monitoring the change in cantilever deflection with the split photodiode detector. The feedback loop maintains a constant cantilever deflection by vertically moving the scanner to maintain a constant photo detector different signal. The distance scanner moves vertically at each XY data point is stored by the computer to form the topography image of the sample surface. This feedback stored by the computer to form the topography image of the sample surface. This feedback loop maintains a constant force during imaging AFM, which uses a sharp tip to probe the surface. Features by raster scanning can image the surface topography with the extremely high magnification up to 1 lakh times comparable to or even better than electron microscope. Measurement of an AFM is made in 3 dimensions: the horizontal XY plane and the vertical Z dimension. Resolution magnification at Z direction is normally higher than XY plane. The atomic interaction at different tip scale divisional distances repulsion. At very small tip sample distances, a few angstroms, a very strong repulsive force is appears between the tip and sample atoms. Its origin is the so-called exchange interactions due to the overlap at the electronic orbitals at atomic distances. When this repulsive force is predominant, the tip and sample are considered to be in contact. Attraction van der Waals. A polarization interaction between atomic and instantaneous polarization of an atom induces a polarization is nearby atoms, and therefore an attractive interaction takes place. The different modes of tip sample interaction when in contact friction, the the cantilever bends laterally due to a friction force between the tip and the sample's adhesion. Adhesion can be defined as the flow energy changes to separate unit area of the two media unit area of the two media from contact to infinity in vacuum or in a third medium. In general, care has to be taken with the term adhesion since it is also used to define force, the adhesion force. Two contact scanning modes, constant force mode, constant height mode. Constant force advantages, large vertical constant force can be optimized to the minimum. Advantage, simple structure, fast disadvantages, requires feedback control, slow response time. Disadvantages, limited vertical range, detector dynamic range, limited vertical range, cantilever bending and detector dynamic mode surface interaction. In the dynamic mode, the tip is oscillated at the resonant frequency. In dynamic mode, the tip is oscillating at the resonance frequency and the amplitude of the oscillation is kept constant. Trapping made imaging. It takes advantages of the contact and dynamic mode. It eliminates frictional forces by intermittently contacting the surface and oscillating with sufficient amplitude to prevent the tip from being wrapped and hence meniscus forces from the meniscus adhesive meniscus forces from the contaminant layer. AFM can work in liquid. A key point for liquid AFM is a transparent solid, usually glass. The space which together with the solid sample surface retain the liquid environment whilst maintain stable optical paths for the laser beams. An optical o-ring can be used to form a big sealed liquid cell. Otherwise, the system can also work in an open all fashion. Quartz glass body, light cantilever block, solvent sample ring. Advantages imaging, advanced imaging techniques of AFM, lateral force microscope, modulation microscope, trapping mode scanning, samples, magnification, SEMO must be conductive, and insulating conductive, SEMO AFM, magnification, two-dimensional, three-dimensional, environment, vacuum, air, liquid, time for image 0.1 to 1 minute, 1 to 5 minutes. Horizontal resolution 0.2 nanometer TEM, 5 nanometer FESCM, 0.0 nanometer for AFM. Vertical resolution N by A 0.05 nanometer and field of view 10 nanometer, some 100 meter. Depth of the field good, poor. contrast and flat samples. Good. Each microscope is very different from another. SEM scans the surface of the sample by releasing electrons and waking the electrons bounce or scatter upon impact. The machine collects the scattered electrons and produces an image. The image is visualized on a television like screen. On the other hand, TEM, TEM practiced the sample by directing the electron beam to the same. The result is seen using a fluorescent screen. Some images are three-dimensional, while TEM pictures are two-dimensional and might require a little bit of interpretation. Check for progress. Space is given below for writing your means we are writing what we have studied in the IR microscopy, spectroscopy, and stretching vibrations, etc. Materials when reduced down to 100 nanometer are called a nanomaterials. The system of the nanomaterials can be done either by top-down or bottom-up approaches. The characterization technique like XRD determines the size and structure of the materials. FITR and UV spectroscopy determines the conformation of the bonds formed in the nanomaterials. STEM, SEM, or AFM determines the size, morphology, and the atoms present in the nanomaterials. Next, properties of nanomaterials in that electronic, dielectric, and magnetic properties. Conductors, insulators, effective mass of the electron, lifetime division length. Examples: hydrogen atom 0.1 nanometer, red blood cell 500 nanometer, carbon atom 0.1 meter, protein 4 nanometer to 40 nanometer, and water molecule 0.3 meter. Terminology. Richard Feynman mentioned in his lecture about miniaturization by evaporation and rearrangement of the atoms, manipulation of systems for data storage down to the scale of the single atomic. After 2.5 decades, a paper was furnished using the techniques of scanning, channeling microscope, STM, and atomic force microscope. The visualization of nano world became a reality. In general, material system with particle sizes within 1 to 100 nanometer range by virtue of possessing large surface to volume ratio come within the periphery of nanomaterials or nanosystems or nanostructure systems. This is because the onset of nanorism differs for different system on the basis of the type of material under consideration. Materials and semiconductors. For example, in the case of a band semiconductors, changes in the physical properties can be observed when the particle size in the range 50 to 100 nanometer, whereas the metallic systems appreciably changes can be observed only when the particle size is much below 500 nanometer. Thus, the observed changes are material system dependent. Next, nanomaterials. In a material, if one of the dimensions is in the range of nanometer, 10 power minus 9 meter, the size of the bulk material can be expressed in 3 dimensions. If only one component of the 3-dimensional nanostructure is of nano dimension, the structure is known as quantum. three-dimensional nanostructure of the nano dimensions. The structure is known as quantum, and the electronic quantum well, and the electronic structure is quite different. When two sides are of the nanomaterial, the electrons surround have large, while area extends in dimension. The material two sides of nano dimension are known as quantum wire. The design and manufacture of extremely small components and systems. In other words, the technology of design, synthesis, characterization, and application of material to nanoscale is called nanotechnology. Scientists and engineers use terms such as following molecular nanoanalysis. It technology that manipulation of individual atoms and molecules is build complicated structures. Nanoscale technology. It is solid state nanoscience that involves self-assembled nanostructures, then film growth and manipulation at nanoscale, as well as nanotechnology to fabricate nano devices, material systems measured in nanometric scale. One quantitative wires, GMR devices, ferrofluids, nano coating sets, bionames technology, QHE, SPM, STM, physics of low dimensional systems, quantum confinement, quantum mechanical unit. Next figure shows entities. Next, semi optical properties of solids, electron conductivity of the material, gap. Already we know that semiconductors already conductors means overlap each other. A small gap is there and large gap is inside. So optical properties of solids, already we know that all metals are opaque or light. Derivation part here. So is equal to V by average time between the collisions of an electron. Lambda is the average distance between the collisions. J is equal to E by M, and VD is equal to 0 plus 8. E to M. If sigma be the conductivity of the metal, then sigma is equal to 1 by rho N is where lambda 2M BF. Let us define mobility. Mu is lift speed for unit for electric field. Mu is equal to VD by E lambda by 2M BF. Sigma is equal to NE E mu E plus NH E mu H, where mu E mu H are the mobilities of electrons and holes. Then sigma is equal to NE E mu E by NH E mu H. Mu E mu H are the mobilities of the electrons and hole respectively. Ne and NH are their numbers per unit volume. The energy gap between valence band and conductor band. Band theory of solids in a metallic crystal. Positives are the arranged in a regular order or periodic order through which the electron moves. Therefore, periodic materials potential field exists. The motion of representative the potential changes from minimum near the centers of the positive ions. The maximum peaks between the centers. The potential changes the minimum near the centers of the positive ions. The maximum peaks between the centers of the so long any line passing through The center of positive events must be a figure. Chronic penning model is also one of the important topics. My electrons in idealized periodic potential. This model illustrates the behavior of an electron in a periodic potential. The behavior of an electron in one-dimensional periodic potential was explained by chronic penning, making simplified model. Potential consists of an infinite row of rectangular potential wells. Let the potential function V of x is equal to 0 for 0 less than x less than a. V of x is equal to V0 for minus V less. Derivation part, we can observe that clearly. Hence, the chronic penny model density of lattice